Welcome back everyone. So, we are studying NPTEL course Topological Phases of Matter. We are studying Berry phase and we have learned Berry phase in terms of states, Hamiltonian, in terms of block states. Then we talked about how a Berry phase is related to band inversion and gauge obstruction in the Hamiltonian, and now we want to take some example to demonstrate that part. And what we will do is this band inversion and gauge obstruction, how they are related to topological invariants. Okay. So, to understand this band inversion and gauge obstruction little more, so let us take some example. So, let us start with 1D and we will do 1D and 2D in details, and then we will see that 1D to 3D, 5D, all these odd dimensions can be generalized easily and the even dimensions can be generalized starting from 2D, 4D and so on. Okay. So, in 1D we had 1k and you have some Brillouin zone minus pi by a to pi by a. Okay. And an electron is electron has a dispersion and it has some band structure, and we are interested in going from any k point, let us take it even at the zone boundary, to here, and the wave function is supposed to be single valued. So, that they are supposed to come back to itself. So, it forms a loop. And now, how this k, a Brillouin zone, is homeomorphic to the parameter space of the Hamiltonian. So, to do that, let us take a 2D two band model. And any two band model can be written in terms of Pauli matrices. Where sigma 1 is equal to, also sometimes called sigma x, and sigma 2 is equal to 0 minus I 0, also some denote by sigma y, and sigma 3 is the diagonal one with 0 and minus 0. So, one may wonder what happens to the diagonal term, which let me write it, then we will see. So, the Hamiltonian then can be written explicitly as dz minus dz dx minus I dy and dx plus I dy, and all of them are k dependent. Then you may wonder what happens to a constant term, some d0. So, what it turns out that such a term only shifts your energy spectrum and does not even enter into your eigenstate. So, that is why this one does not change anything in our topology. So, we generally just set this to be 0 for simplicity. Okay. So, what I am rather saying is, if I look into the energy eigenvalues and we will denote it by plus minus, can see that the band is splits into two bands, and this is being the constant shift, okay, and the eigenstate will, as I said, is just a matter of notation, and I am not including the block phase part here, and just a notation, just turns out to be 1, and this is e to the power minus I phi, where phi is now this is the part I will come back. This is only true when dz equal to 0. For other dz will use, but even when you will have dz, you will see that the eigenstates do not depend on d0. So, I will ignore this. And now what we will do is that I have a one dimensional space, okay, and it is a loop, it is actually S1, right. So, this is equal to homeomorphic to k as a some sort of a periodic, and so this is S1. So, this Brillouin zone 1D B zone is just S1, right. And now, I want to draw a S1 in this parameter space. So, now for simplicity again, so if I have all three of them, I will have dx, dy or dz, and then some S2. If I take a general dx dy as dz, but right now I am interested in this particular 1D case, I am interested in S1. So, let us take a S1 in which let us set dz to be 0 for simplicity. Okay. The point we are going to make is can be met without taking dz. All right. So, then I have a k going from minus pi by a to pi by a, and then I am going to the space of dx and dy. Now, notice interesting thing. It says that this is just a, it does not depend on dx dy explicitly, only depends on the radius in this D space, okay, and the eigenvalues only depends on the angle. Okay. So, each eigenstate then sort of and both eigenstates are on top of this curve, right, and this phi denotes the eigenvectors with a plus minus that differentiates the two states. Now, the question is this is also S1 and this is also S1. So, I have a homeomorphism from the Brillouin zone to this. Now, what is the d equal to 0 point? So, d equal to 0 point is a degenerate point. When d equal to 0, the two states are completely degenerate. So, if I draw the band structure, E plus E minus, and when d equal to 0 they become so degeneracy is a point which we will see again, is a point where any linear combination of these eigenstates is also an eigenstate. Okay. So, that is the point we want to remove for the time being. So, we will go back to the point where they are in in fact, we will show quickly that when d equal to 0, the Berry curvature or Berry connection becomes singular, becomes infinite. Okay. And that infinite point we want to remove. So, now you will have two situations, one in which as the electron moves from here to there or going from in a given band here to there, we encircle the eigenvectors encircle this loop, and it encircles a point which is a singular point, and you do have a non-trivial loop. This loop cannot be contracted to 0 because it encircles this point, and your phi will change phi plus 2 pi as you encircle this, we encircle a 2 pi point, versus a situation in which this is still this, in which the circle it encloses is somewhere here instead of here. So, now you see that any point phi, as you go around it, phi changes to phi, you just come back to same point, it does not change by 2 pi because you just think of it as like this. Another way to say, which is harder to show it here, on this sort of S2 manifold you have not really gone all around it, rather you have you have gone to some value and then come back, you have not gone all around. Okay. So, this is the case which is non-trivial, and this is the case which is trivial. Okay. And now we can see that mathematically. We said that those two eigenstates are okay, and phi was the angle, and now we can compute it, and let us compute the Berry phase for minus, which is u minus del k u minus state and with algebra it can be shown, yes, it can be shown, I think it will be half times del q how much the phi has changed as you go in the Brillouin zone from minus pi by a to pi by a. In the first case we get nothing, delta phi is 0. In the top case delta phi is 2 pi. You can wrap twice or n number of times. So, what we can do is that we can just divide by this factor of this 2 will go away. Will be 1 for non-trivial case or n called the winding number equal to 0 for trivial case. So, the non-trivial case is again when we wrap the d equal to 0 point. So, non-trivial, and the trivial case is when we are somewhere here. If you wrap the opposite way, then you will get a minus n, and this is the winding number. So, this is the topological invariant. Okay. We will take more specific example called SSH model to show that how different parameter space allow us to define this and this. Right now we take a 2 by 2 Hamiltonian which is general, and the Hamiltonian we wrote dx minus I dy dx plus I dy. We can always also write it as some variable q, a function of k, and q star. So, then this winding number for minus 1 band, we can write it as, so q is dx minus I dy is equal to d e to the power minus I phi. Can be written as q inverse del q q dq. Okay. And that is why the magnitude disappears because of this q inverse term. So, that is why remember when we take two states and we said that we just care about the phase difference between those and the amplitude do not matter, and here it's one example showing that it's the phase difference between the two states, the phase winding between the two states that matters, not the amplitude. Okay. So, this was in 1D. And one more thing we will show is that proportional to 1 over t, okay, which goes to infinity at. So, things are not well defined when d equal to 0. So, that means when the two bands are degenerate, and we are right now avoiding those points. When two bands are degenerate, this point will be here, okay, and that is this point, which is a degenerate point. So, this is the point that creates the singularity in the theory. So, in this case we are wrapping around the degenerate point, although the system does not have the degeneracy. In this case the band structure was like this, right, with some band inversions between them, but there is no degenerate point. At some point here there is a band inversion has happened, but and what it does is that we have some band alright. So, there is a band inversion has happened. So, it goes from one band to another band, or it goes from plus band to minus band, or if you stick with one band, the eigenvector has changed from this state to that state. Around this point, but it still has not seen the degeneracy, it just wrapped around the degenerate point, and degenerate point is a singular point, kind of a monopole point, right. Whereas in the second case there was no band inversion, it is always blue here, it is always green there, and we can, and that is nothing but we do not wrap the degenerate point anymore. So, no band inversion has happened, we just go around some trivial directions. Okay. Let us do this now for 2D, and we will call such a topological invariant as Chern number. Okay. So, 2D means we have a Brillouin zone kx, ky, and as we did earlier, these directions and these directions are same, and these directions and these directions are same. And what we do is that we wrap these two directions, which makes a cylinder, and then we wrap the end of these two cylinders, and what we get is a torus. Okay. So, we move to torus. And now we want a parameter space of the Hamiltonian in terms of 3 of them, and we will get a sphere which is S2. So, this torus will be homeomorphic to S2 in the Hamiltonian parameter space, and this is called block sphere. So, the eigenstates are now denoted by all the points on this constant D sphere, and this is called block sphere. All the eigenvectors will correspond to these points, and D equal to 0 will again be a degenerate point. Okay. So, let us see that. Energy eigenvalue will again be plus minus D, which is now 3 of them, D1 square, D2 square, D3 square. So, I will keep on using dx, dy, dz or d1, d2, d3 adjust the notation, and different books use different notation. So, as you can see that in many places I change it to dx, dy. Okay. And the same thing also. Okay. And this sort of change of notations will keep on happening, because notes are taken from different books and different books use different notes. I want to save x, y, z for the k and use d1, d2, d3, at least try to use in most places when the confusion does not may arise, as d1, d2, d3. Okay. All right. And the eigenvectors. And these eigenvectors are slightly more complicated looking. Plus T3. So, in fact, I can use the same notation . Recall that this can be written as d to the power minus I phi d parallel. Okay. Whereas these are kind of trivial, or one can also write it in terms of d1 is equal to again d cos theta sin phi, d2 equal to d sin theta sin phi. The way I define it's cos phi d3 equal to d sin theta with two polar coordinates, and this will give you the winding. So, this will be the theta, and then this is the phi in the dx dy plane. So, then I have to use this will be the angle in the dy d1 d2 plane as we did in 1D case, and now we will have one more direction, and then we will have a block sphere. Okay. So, now if you compute it, what we will find is interesting. Okay. And mu is equal to x and y. So, what we can also write it as 2d d plus minus d3 epsilon ab d dA mu dB, where ab is 1 2. No, yes, 1 2, not 3. Okay. And so, you need to take one more derivative of the connection, and you will find A B C dA, excuse me, dB nu dC. So, now you see that this is like this, or let me write it explicitly. Let me still keep it. So, this is in 2D, that will be d dot del kx d del ky d. The solid angle, I can divide this d for each one, and then I will have. So, let me do it this way, so that we can use both the formula. I want to, if I cross it, then I will have the unit vectors. So, then this is like a solid angle in that D sphere, some solid angle okay. And if I keep the D, then you can see that this is a singular point, and this is indeed the formula that we obtained for monopole, in which case it was 1 over r square or r cube. If I take all the D, which are kind of your positions, then you will have r cube, or otherwise r square if I normalize the first one. That is what one does. This is along the z direction, then this is along x and y. So, then it is 1 over r square, and that is the magnetic field for a monopole. So, here indeed now we see that D equal to 0 point, it is like there is a some very monopole is here, sitting here, which is at the degenerate point. Remember, d equal to 0 is the degenerate point, and now we are going to compute the flux of it along all directions, and this is my solid angle in the d sphere. Otherwise, it is the curvature or magnetic field through this 2D zone or through this torus. Okay. And here if you choose this is to be kx ky, then this is nothing but kx ky, or sometimes it is called the magnetic field is being along the z direction. Okay. And in the block sphere it is like radiating in the across the block sphere in the Hamiltonian parameter space. Okay. So, then we will have the Chern number, which is nothing but the flux of the very curvature, right. And just writing those expressions, we get 1 over 4 pi do not get too much confused with all this. So, notation just the right. I think the reason I am using this notation is something that we should be able to use to generalize this. Okay. And x y are related to this x y. So, then this one so this is the flux and this is the area under this flux to get the total flux density, and this is the flux, whereas in 1D we had a phase winding and this was the line integral. This is some quantity related to this and the line integral. So, it is kind of a vector potential or connection, Berry connection, and this was the line integral of the vector potential. And in 2D, now 1D is generalized to 2D and becomes area, and this becomes the flux, which is F. So, now if I go to 3D, what do I get? So, 1D should generalize to 3D, the area should become volume, and what will become here? It should become volume element, and earlier we had connection, now we will have connection times curvature. Okay. And 4D, again 4D volume area, 4-dimensional area, and F and so on. Okay. And that is what I want to do. So, I am not going to derive those things in high dimension, but I am making this analogy and one should be able to see these expressions. Higher dimensional topological invariants. Okay. So, for 1D, we find this line integral of the connection. So, in 3D, some normalization is there to make this an integer, and we will have the connection times the curvature. Okay. Or there is actually a antisymmetric product, because volume is an antisymmetric product. So, the integrand is also antisymmetric, and you can write it in this way: mu nu rho, a mu rho nu, and a rho nu, and partial derivative with respect to nu and a rho, and that is nothing but the curvature. And then you can generalize to higher dimensions. So, 5 dimensions, so you will have 5 antisymmetric product between A and 2 curvature, and you can generalize to any higher dimension, and all of them are odd, because you can only define an odd integral of this point. So, kind of a line integral goes to volume integral and so on, and you will have one connection and the curvatures. So, one connection, and then you will have all the other curvatures in some higher dimensions, okay. With the Levy beta or kind of a wedge product, if you do it in a more mathematical way, because these are the forms antisymmetric. We remember that these are sort of the antisymmetric tensor, right. So, they are multiplied by the antisymmetric curvature measure, which gives us the n. And we had d1 minus I d2 in 2 dimension, and you can generalize to high dimension. And for chiral Hamiltonian, and we have not defined what is chiral, and we will define later. For any chiral Hamiltonian, we can always bring it to all chiral Hamiltonian into this form, which are purely block of diagonals, and these are matrices, u n matrix or u n by 2 matrix, if it is a n by n. And in such case, the winding number 1, we showed that it is q minus q, derivative of q, and now for higher dimensions we just have to take a trace, and then if you go to have a higher dimensional Hilbert space, it will be like this, still single derivative. For higher dimensional Brillouin zone 3 dimensions, again you have to do the same thing with antisymmetric product kx, ky, kz, and then take a trace. So, here already I have made it to be antisymmetric, but otherwise we have to do it with respect to this, and each one will correspond to the derivative of this q matrix along all the antisymmetric directions, and you will have a volume integral. And then we can do the same thing for even dimensions. We talked about Chern number, which is a total flux passing through the 2D Brillouin zone of the Berry curvature, and for 4 dimension, which is we will not use it for our 3D Brillouin zone, but in some cases we may use it. So, it will be again an antisymmetry product of 2 curvature and a 4 dimensional area integral, and you can generalize to higher dimensions. It will be again product of the curvatures and area. And for certain Hamiltonian, for higher dimensional Hamiltonian, instead of Pauli matrices, if those Hamiltonian can be written in terms of gamma matrices, okay, which anticommute with each other, and there will be certain class of Hamiltonian which we can write, and we will talk about that when we will talk about symmetries. But if you can do that, then again we can write the Chern number in terms of in the D space as the solid angle in the corresponding n sphere with the antisymmetric one, that will, and then the area. Okay, this is for 4 dimensions. Yes. Okay. So, we will mainly be using the winding number in 1D, Chern number in 2D, and again winding number in 3D. In some 3 dimensional time reversal invariant cases, the other one are more of a mathematical exercise for us. So, with that we complete this week's syllabus, in which we wanted to understand the mathematical definition derivations of Berry phase, and then how does the Berry phase translate into derivative of the Hamiltonian and then Bloch states. Then we relate the Berry phase into gauge obstruction and band inversion. Then we have talked about the band inversions in 1 dimension giving rise to winding number. Then we talked about band inversions leading to Berry curvature in 2 dimension, and then we generalized in an ad hoc way to higher dimensions. In the next chapter, week 4, we will take specific Hamiltonians like SSH Hamiltonian, Kitaev model for 1 dimensional case to demonstrate how real Hamiltonian give rise to winding number and Berry phase. And then we will take also 2 dimensional examples like Rice-Millet model, graphene and so on. We will talk about the insulator case as well as the degenerate case, which leads to Dirac cones and Weil cones and Dirac nodal line and so on. With that, I stop here today. Thank you very much for your attention.